I will begin with a word of prayer once I get this out of the way. Okay. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today, help us to glorify you what we do and understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So we were talking about the case that V is equal to W1 direct sum W2 direct sum WK, all right? In this case, we say V is internal direct sum of subspaces W1 through WK of V, all right? Now, in order for this to make sense, we need that these subspaces are independent, and I talked to you guys about 5 equivalent ways of capturing that independence, right? But there's one last thing I need to talk to you about with this material, which is what happens if we have a linear transformation, right? So here's a definition. If T is a linear transformation from V to V, and W is a subspace of V for which T of W is a subspace of, well, we don't even need subspace, we could just say subset, right? It is true that that automatically implies that T of W is a subspace of W, because we know that the range is a subspace. All right, so like, but all we need to check is that it's a subset, all right? So if the range is a subset of W, then W is an invariant subspace of T, right? Also, T sub W, a mapping from W to W, is defined by T sub W of X is equal to X. Equal to X, listen to me, no. Equal to T of X for all X in W. So like T sub W, basically, it's I would say it's the restriction, but why is it not just the restriction? So like if I had T restricted to W, how's that work? What's our definition? We chop the domain down to W, but what's the codomain? By our definition of restriction, we don't do anything to the codomain. The codomain just stays what it is, right? So the restriction of a linear transformation to the subspace is a little bit different. This T sub W, we're simultaneously messing with both the domain and the codomain for our new map, right? But it's obviously very much related to T. It's just whatever T does to W. Now, why is that? That's well defined for an invariant subspace. Why? Like in order for this T sub W to make sense, we'd need the outputs to again be in the codomain, right? But that's by assumption up here, right? T of W is subset of W. So like this is a reasonable thing to define. And of course it's linear, all right? Okay, so here's the basic theorem. If T of W sub I is a subset of Wi for I equals to 1 to ... k, and you know V is equal to the direct sum of W1 through WK with bases beta 1, beta 2, beta k respective. For W1, W2, WK respective. Don't question my grammar. Then, if we form the basis for V as like 1 union 2 union K, and we're putting them in order. So we're putting the basis, the part of the basis that's in W1 first, the part of the basis which is for W2 second, the part of the basis which is for W3 third, and so forth, all right? Like, remember, a basis is an ordered set. Then, the matrix of T with respect to this basis is the matrix of the T sub W1 with respect to beta 1, direct sum the T sub W2, beta 2, and so forth. In other words, the matrix is block diagonal, where the blocks are particularly the matrix of the T sub W's, the restriction, well, I say restriction, but it's not quite restriction. I need a word for these T sub W's, but I'm just going to call them T sub W for now. Do you guys remember what we meant by direct sum of matrices? This means we're talking about a block diagonal matrix, right? Like this looks like M1, M2, M sub K, right? Where my, like, M sub J is the matrix of T sub Wj with respect to the beta J basis. Now, you know, this is one of those places where my notation is not great, but I just, okay, so like, we should have the talk. If you guys want to use T sub beta as a shorthand for T sub beta beta, I'm not going to complain. You can do that if you like. I slavishly devote myself to T beta beta as to be consistent with the larger discussion about coordinate change. Yeah. But you can see in this that I've written redundantly beta sub 1, beta sub 1, beta sub 2, beta sub 2, beta sub k, right? Every time I write the basis, I write it twice for the matrix because I'm in the habit of writing the basis for the domain and the basis for the codomain. But you can see that you have all the information you need with just one beta, right? Because what do we agree to in this part of the course? We're going to use the same basis in the what? In the domain and the, it's kind of squirting today. I guess hey, it's squirting again. Whee! It's come back to life. You guys ever seen Awakenings? It's a movie about Alzheimer patients. Robin Williams stars in Before You Were Born. It's okay. Go watch that movie and think of the patients in Awakenings as my spray bottle. I could probably find a better analogy. Maybe I'm sure you could. But my spray bottle was not working earlier. All of a sudden it started working again. Woohoo! Sort of working. I cleaned this board earlier so that this wouldn't happen. But obviously, someone found the eraser. I should have thrown that out. All right, so that's basically it, guys. If we have invariant subspaces, right? Then if we have V as the direct sum decomposition of invariant subspaces, it's especially nice for how the matrix works out. All right? So if we can find invariant subspaces for a given transformation, that means that we can much better understand the structure of it, and that's what we're going to see. We're going to see that eigenspaces are just this kind of thing for linear transformation. That said, I wanted to just say a word or two more about examples, or just actually more about notation. So you guys know the complex numbers are what? We can write them like a plus ib, right? Well, another way you could write this, like I talked about in the notes, is you could say r direct sum IR. And if I write that, what I mean by that, this notation, what I mean here by this equality is actually that okay, so first of all, I guess I should be a little bit more transparent here. We could also think of this as a comma b, right? And I would say that's r plus IR. And so like this notation I'm suggesting, it suggests going from here to here that like, a plus ib is a times 1 comma 0 plus b times 0 comma 1, right? In other words, I'm using this for 1 and I'm using this for I. That's the notation. And so that's also what I mean down here. I'm saying that when I write that, I'm saying that like, so by the way, like here's another notation. VR is just a sneaky notation for like span sub r of v. All right? So just, if you allow me this notation, I could give you another example. What I call the three hyperbolic numbers have the form r plus jr plus j squared r. And so this is as a point set, it's R3, and I'm using a special notation. You see, I'm using the notation basically E1 is 1, E2 is j, and E3 is j squared. So like if I had a three hyperbolic number a plus bj plus cj squared, that is, you could write it as a b c if you want to go back to like R3 notation. Anyway, this becomes a more interesting example later when we think about like algebras and stuff. All right. Okay. But anyway, I wanted to mention this notation just to give you an example of kind of like the other way around. So the examples I gave you last time, I'm like, here's a vector space, here's subspaces. We can prove that those subspaces are independent, and so we have an internal direct sum. Here I'm saying, by writing that, I'm communicating to you that this vector space C is the internal direct sum of a real part and an imaginary part. Or this, the three hyperbolic numbers, it's the direct sum of a real part, an imaginary part, and a j squared imaginary part. Okay, those aren't really terms, but anyway. So enough about that. All right, so just wanted to say a word about that because it's in the notes, and I do on occasion talk more about these examples. I mean, it's kind of a funny thing, but like, what is an algebra, by the way? So we talked about vector space, right? We talked a little bit about like the difference between ring and a field, right? At the start of the course, like a field, every non-zero thing has a multiplicative inverse, right? A ring doesn't have to have that, right? Like Z6 is a ring, 2 times 3 is 0, but neither 2 or 3 is 0, right? What is an algebra? Well, an algebra is a vector space paired with a multiplication, right? So H3 defines like an algebra. If we basically have the rule that we multiply like normal, and we have the rule that j cubed is 1. This defines the algebra of the three hyperbolic numbers. Complex numbers is an algebra defined essentially by I squared equals to -1, and you know the rest, right? We multiply like normal. So anyway, this is a bigger question is like, well, how do you study algebras? What can you say about algebras? And so you guys are going to take a course in modern algebra, right? Or modern abstract algebra. I forget what our title is. Depending on where you take that course, different schools will call it modern algebra or abstract algebra. I forget what we called it. But here's the great irony. We never define algebra in abstract algebra. Not until Math 422, actually. So it's kind of a funny thing. Because we talk about groups and rings in there, but we probably maybe even talk about fields a little bit. But we're not going to talk about algebras in the abstract algebra course, which I think is, to quote Dr. Wang, ironical. So, but now you know what it is. An algebra is simply a vector space paired with a multiplication. It's a way to multiply vectors and get new vectors. That's an algebra. All right. I now have digressed wildly. Let me get back on track here. So I wanted to talk to you guys, for the most part today. Somebody gave me a sticky surprise attack mission 5 in differential equations just now. It's got something sticky on the front. That's very I need to modify my deduction schedule to include minus 20 for stickiness. Do you think? I think so, right? Yeah. It's unpleasant. Before I forget, there you go. All right, so here we go. So let us begin our discussion of eigenvectors and values, right? So I think I'm going to begin with a definition, if that's okay with you guys. So definition, given V over F, a vector space, and we're gonna say finite dimension for this part of the course. I do think, well, this should probably be on my list of things to do, which is to think about how many of these theorems can immediately be extended to infinite dimensions, because there is a good chunk of what we're doing here which still makes sense for infinite dimensions. However, other parts definitely not. So like some of what we're doing is going to involve the matrix of the transformation, and in as much as we're using the matrix of the transformation, you can probably extrapolate from that it's probably not probably not good for infinite dimensions. Okay, anyway, so finite dimensional vector space and T, a linear transformation from V to V, we say, let's say X in V, X not equal to 0 is an eigenvector with eigenvalue lambda in F if T of X is equal to lambda X, right? So that's the definition of eigenvector and eigenvalue. So like theorem, well, forget the theorem. Let's just work on it. Consider T of X is equal to lambda X if and only if what? T of X minus lambda X is equal to 0. which we could rewrite as t of x minus lambda times the identity acting on x is equal to 0, which we could rewrite as t minus lambda times the identity acting on x is equal to 0, right? So we could just as well trade this out for the characterization t minus lambda times the identity acting on x is equal to 0, right? I would take either as the definition. They're pretty much the same thing, right? So proposition t has eigenvalue lambda if and only if the determinant of t minus lambda times the identity is equal to 0. I'm still assuming that t is a linear transformation on a finite dimensional vector space, okay? So let's prove this way, right? So there exists x in V such that what? T of x is equal to lambda x, right? Hence, t minus lambda times the identity acting on x is equal to 0. So thus, the kernel of t minus lambda times the identity is not equal to 0, right? But if beta basis for V, then the null space of t minus lambda times the identity with respect to the beta basis is not equal to 0, because we know that the kernel is mapped to the null space of the matrix, right? And what does that mean? Well, that tells me that this matrix is not invertible, right? If it's got a non-zero null space, it can't be invertible. In other words, by 221, the determinant must be what? Zero, right? The determinant of that matrix must be 0. It has to be a singular matrix. But how did we define the determinant of a linear transformation? Remember, the determinant of a linear transformation is defined to be the determinant of the corresponding matrix with respect to any choice of basis. It matters not which basis you choose, the determinant's the same because they're all equal up to a similarity transformation, which is to say that this is the determinant of t minus lambda times the identity equals to 0. But I would point out to you guys that these steps are reversible. See, this and this are the same. And if this is equal to 0, it's that not being 0, right? And likewise, up here, just the last this last part here. Let me talk about this. Notice that if the kernel of t minus lambda times the identity is not equal to the 0 subspace, what does that mean? There exists x not equal to 0 such that what? T minus lambda times the identity acting on x is equal to 0, right? Because it's in the kernel. But that means that t of x is equal to lambda x, right? So in fact, all of the arguments I just gave you are reversible. And so there you go. This is the deal. We have an eigenvalue if and only if we have a 0 to the so-called what? Remember? We talk about this in 221, yeah? The definition. P of t is equal to the determinant of t minus t times the identity. Or if you like, this is the characteristic polynomial. So another way to restate my proposition is just this, right? Lambda is eigenvalue of t if and only if what? P of lambda is equal to 0 for P, the characteristic polynomial. Now once you try to really wrap your noodle around this, you'll at some point or another go, wait a minute, is it possible to have an eigenvalue for which you don't have an eigenvector? Is it? Is it possible to have an eigenvalue for which you don't have an eigenvector? I mean, setting aside, so that already begs some significant questions in terms of our definition, because we've defined eigenvalue and eigenvector together, right? They're a package deal. But could you separate it? Could you somehow have a 0 in the sense of, could you have a 0 to your character? Let me state it more precisely. Could you have a 0 to the characteristic polynomial and yet somehow not have a vector, a non-zero vector, such that t of x is equal to lambda x? The answer is no. These calculations show that. If you have a 0 to the characteristic polynomial, you automatically must have at least one non-zero vector such that t of x is lambda x. And I mean, the argument for that is simply that, you've got determinant of t minus lambda times the identity is equal to 0, right? That means that this is not, one-to-one, not injective. Which means that the kernel of this thing is not equal to just 0, because if it was, it would be 1-to-1, as you guys proved on the test, right? You saw that it was a thing you could have proved on the test. Now, it was just t on the test, right? It wasn't t minus lambda times identity, but the point remains, right? So, and that being non-zero is tantamount to t of x equals to lambda x, right? Some x not equal to 0. So I hope I've proved my point. Right? There's a one-to-one correspondence between zeros of the characteristic polynomial and eigenvalues of your transformation. All right? Agreed? I hope. So next thing I should probably define, if I can, is what do we mean by like a polynomial? Well, first of all, what's a polynomial? You guys tell me. What's a polynomial in T? What's that mean? Poly means many. Nomial means, well, nomial? No, I think term, right? Polynomial basically means many terms.
It's an expression with multiple variables, isn't it? Like x squared minus x plus 1.
X squared minus x plus 1. Yeah, for me, a polynomial specifically means something of the form like C0 plus C1t plus C2t squared plus, I mean, what you were saying is not wrong. It would just be like an unsimplified polynomial, right? But we can always write a polynomial in terms of the sum of monomials, right? Or sum of power functions with weights, with coefficients which are taken from the field. That's what we mean by polynomial, all right? Like this is, I have a notation for this. This is an element of f of t. So this is just a fancy notation for the set of all polynomials in t. And here, the degree of p is equal to n, provided what? C sub n is what? Not equal to 0, right? So the degree is defined by the leading non-zero term. All right? Now, so what would we mean by p of big T? What would that mean? If t is the linear transformation we've been talking about, what do we mean by p of t? So what we mean is you replace C0 with C0 times the identity map, all right? And then C1 times T, and then C2 times T composed with T, you see? And then so forth and so on until finally you get Cn, T composed with T. This is n-fold times, right? But we don't usually write that. What do we write instead? We simply write t to the n, right? And we simply write t squared. And sometimes over here, we simply write c naught, right? Like notational option. You could write determinant of t minus lambda times the identity. If you're willing, you could write it as t minus lambda. All right, so this is an accepted shorthand, right? I've graded your test, so you probably already somewhat feel the sting of unacceptable shorthands. But anyway, not so much on this test, though. So this is a polynomial of the transformation. What can you tell me about p of t? If t is a linear transformation, what is this? We're talking about a sum of linear transformations, right? Because remember, a linear transformation composed with itself is still linear. We proved that. So this is actually, again, observation. P of t is itself a linear transformation from v to v, for what it's worth. All right. So we can work with polynomials in the operator. And that's one of the things we're going to do throughout this material to process it, to understand it. So what do you guys think an eigenbasis is? What does it mean to have an eigenbasis?
Basis for the eigenspace.
Yeah, so definition, beta is an eigenbasis for t, which is the v to v linear over f, right? If beta is equal to v1 through vn, where t of v sub j is equal to lambda j vj for j equals to 1 to n is a basis. For v. In other words, it's just what I think what Jonathan said, which was an eigenbasis is a basis of eigenvectors. Right? Now it's important that the eigenvalues be taken from the field. Did I write that? I didn't write that. Oopsie. My bad. Lambda j is an element of the field, right? That's important. There are examples, right, where the linear transformation, if we think of the vector space as being a real vector space, it doesn't have an eigenbasis. But if we think of the vector space as a complex vector space, then it does have an eigenbasis, all right? So that brings us to the following theorem, which is pretty important in the big scheme of things. So, and here's the theorem. T is diagonalizable if and only if there exists an eigenbasis for T, all right? And again, the context here is T is a linear transformation on a finite dimensional vector space over a field, which is given, all right? You could say T is a endomorphism. An endomorphism is a linear transformation from a vector space back to the same vector space. Endomorphism equals linear transformations on V. Okay, anyway, so, yeah.
So do we have a use for a supposed eigenbasis that uses things that are outside of the field?
I mean, I will eventually talk about taking a real vector space and complexifying it, so there, yes. But more broadly speaking, the problem is how do you extend a field? Well, that's a problem for Math 422, unfortunately. So it is, as many things are, above our pay grade. So here, would you guys, let's start with the converse direction, yeah? Let's go this way. And by the way, what does it mean for T to be diagonalizable? What should that mean?
There exists a similar matrix that is diagonal.
T is a transformation, though. So your heart's in the right place, but let's say there exists a basis for which the matrix of T is diagonal, right? Yeah. So that's our goal, is to show that the matrix of T is diagonal. But let's start with the eigenbasis. That's what we're given, right? So assume beta equals to V1 through Vn with T of Vj equals to lambda j Vj for j 1, 2, all the way out to n. All right, then T of beta beta, how do we define that? Well, you guys remember, that was T of V1, calculate the beta coordinate of that, and so forth and so on. The T of Vn, you calculate the beta coordinate of that, you know. All right, but what is T of V1 is, well, that's lambda 1 V1. You know, we're supposed to calculate the beta coordinate of that guy. Lambda n Vn, calculate the beta coordinate of that guy. Right? Well, what is the coordinate vector of, you guys know how this works. So what that is lambda 1 E1. And then you'd get lambda 2 E2 all the way out to lambda n En, which in a more transparent notation is lambda 1, lambda 2, lambda n, which is diagonal. So if we have an eigenbasis, the matrix with respect to the eigenbasis is a diagonal matrix. So what about the other way? Suppose we'll use gamma just to try to remove any possible confusion. Suppose gamma is equal to W1 Wn such that what? The matrix of T with respect to gamma is diagonal, right? And we'll call the diagonals D1, D2, Dn, right? So suppose T is diagonalizable. In other words, there exists a basis gamma such that the matrix with respect to gamma is the diagonal matrix with D1 through Dn on the diagonals. What does this mean? Then, if we look at the matrix of T, excuse me, the coordinate vector of T sub Wj, right, with respect to gamma, what's that equal to? Well, it's equal to D sub j Ej by the given T gamma gamma, right? Do you guys see that? So that is the jth column of my matrix. By definition, it's the coordinate vector of the jth basis vector. Yeah. But what does that tell you, though? Can you guys tell me? What does that tell us about T of Wj then? If I take the inverse coordinate map of that, what's phi gamma inverse of dj Ej equal to? Well, it's dj phi gamma inverse of Ej. What is phi gamma inverse of Ej? It's Wj by construction, right? That's how the basis works. It maps the abstract basis to the standard basis and vice versa. So this is immediately giving me that T sub Wj is in fact dj Wj. Which means what? Gamma is eigenbasis. With, eigenvalues what? D1, D2, dn, right? And that's my theorem, is that T is diagonalizable if and only if T has an eigenbasis. And there's a little bit more. What can you tell me on the basis of our proof? If it's diagonalized, what's the nature of the diagonal elements? What are the diagonal elements? Those are exactly the eigenvalues, right? So this should all be familiar from Math 221, but there's a significant difference in what's happening here. We are proving all of it, right? Some of this, at least when I teach 221, I just state, at least I try to just state it. Sometimes I get sucked into proving stuff in 221 and then I have regret. There have been earlier parts in this semester where I have tried to prove something in 221 and then I just stated it in here, and then I was like, wait a minute, I've got everything turned upside down. I should have proved it in here and stated it in there. What's wrong with me, Many things, I suppose, but so that brings us to our definition. Given, T, endomorphism, a linear transformation on V, and, lambda in F, an eigenvalue of T, we define, I think my notation in here is E sub lambda equal to the kernel of T minus lambda. You'll forgive me if I stop writing the id at this point. I'm tired of it. This is a subspace, right? Tell me what you know about its dimension. The dimension of the kernel of t minus lambda. What can you tell me about it? Can it be 0? It cannot. We proved it has to be 1, right? There's always at least one eigenvector for each eigenvalue in the sense of being a 0 of the characteristic polynomial. So we can put a 1 down here, right? So this right here is what we call the geometric multiplicity. Geometric multiplicity of lambda. All right? Now, I don't have time to prove it today. But what we're going to show is that this is bounded above by what I might call m sub lambda, which is the algebraic multiplicity of lambda. Now, the algebraic multiplicity concerns the number of times the factor t minus lambda appears in the characteristic polynomial. Right? So like, so this is, I'll just say it's based on the characteristic polynomial of t. So can you guys tell me any particular theorems about eigenvectors that you remember from the previous course? First of all, everything we're saying here we can also say for a matrix, right? We can talk about a given matrix A, the eigenvectors of A, the eigenvalues of A, right? The eigenspace of A. All of this stuff works for an n by n matrix over the field. So that's one thing. I haven't written any of that. I'm just focusing on linear transformation because that's what's new. But if you read the notes, I have replicated like all of that stuff we said about n by n matrices in 221. It's there too to remind you guys. Let's see here. So if I have different eigenvalues, right? If I told you I have vector v1 with eigenvalue lambda 1, and if I have vector v2 with eigenvalue lambda 2, what could you tell me if lambda 1 is not equal to lambda 2? What could you tell me about v1 and v2? So here's a theorem. If we have v1, v2, vk with eigenvalues lambda 1, lambda 2, lambda k distinct, all right, then the set v1, v2, vk is linearly independent. So one of the things I want to prove next class is that if you're, what we're going to see next class is that if v is equal to like e1 plus let me not try to do that on the fly, but I'm going to mess up the preconditions or something stupid. But I want to talk to you next time about the independence of eigenspaces, basically. And like the fundamental instance of this is just when we have independent, if we have eigenvectors, if they've got distinct eigenvalues, they're independent. But this actually extends to the eigenspaces as well, as we'll see. So the most basic case of this, we've kind of already been playing around with. Like, if I had C1v1 plus C2v2 equals to 0, like how would you prove, given that, you know, T of v1 is equal to lambda 1 v1, and T of V2 is equal to lambda 2 V2, right? Suppose you know that. If we assume this, can you prove to me C1 and C2 are 0? How would you do it? What I would do is I would like, say, T minus lambda 1 and let that act on this, right? What's that do? So like you have T minus lambda 1 acting on V1 times C1, T minus lambda 1 factor out the C2 acting on V2. What happens here is you get lambda 1 V1 minus lambda 1 V1, also known as 0. And over here you get lambda 2 minus lambda 1 acting on V2. So this is 0, but this over here is what? Remember, these are distinct, which means that their difference is not 0, right? So that implies what? That implies C2 is equal to 0. But then what? C1 V1 is equal to 0, which tells us what? That tells me that C1 is equal to 0, since V1 is what? Not equal to 0 by assumption. I should have said that, obviously. I'm saying that these are eigenvalues. If those are eigenvalues, then those are non-zero vectors, right? And therefore what? Therefore V1 comma V2 is linearly independent. All right? So I can prove distinct eigenvectors with distinct eigenvalues are necessarily linearly independent. And if you understand this proof, it's easy enough to like bootstrap it up to 3 vectors or more. You just like operate by not just T minus lambda 1, you operate by like T minus lambda 1 and T minus lambda 2, and that'll get rid of everything except for the third one. Anyway, I have a gory, horrible proof in the notes where I do this for K1s in terms of, you know, product of everything but one thing. But anyway, I think that's it for today, guys. So I just for the retest Monday. Oh, I'm sorry, I went way over.